tempted to ask you top questions.
Way more than
Today, if I were to give today a name, today is Air Resistance Day. Air Resistance Day. Most of the day is going to be spent on air resistance. Up till now, we've always had free fall where we ignored air resistance. Well, we're not going to ignore it anymore. So we're going to answer a couple of questions like who hits the ground faster, the fat parachutist or the skinny parachutist. We're going to talk about if I shoot a bullet in the air, what's the best way to shoot that bullet in the air? Should I shoot it horizontally or vertically? And we'll talk about how air resistance affects that. But first we're going to talk about why all objects fall at the same rate, how Galileo was able to convince his fellow scientists that all objects fall at the same rate. So here we go. All objects fall at the same rate. Of course, ignoring air resistance. So Galileo, he went on the top of a famous building. Do you remember that building, what that was? Wait, what? Which building?
The Derby side, like the Leaning Tower.
Absolutely, the Leaning Tower of Pisa. Yeah, and it was called the Leaning Tower of Pisa because it was made entirely of pizzas. The first floor was pepperoni, the second floor was sausage, third floor was Hawaiian, you know, they had pineapple. So you've got this Leaning Tower of Pisa. No, actually it's pizza, I just want to let you know it's not pizza. Okay. And so he's standing on top of this building, you know, having identical lead ball and wood ball and dropping them, and supposedly they're hitting the ground at the same time. And his fellow scientists are wowed by this fact because all scientists believed before Galileo that heavy things fell faster than light things, and almost to the point of a proportion where something twice as heavy would fall twice as fast. How do you know? Because when I take an ant and I drop an ant, it takes a really long time to hit the ground, whereas if I take a rock, it takes a pretty short time for the rock to hit the ground. So since the rock is heavier, it hits the ground faster. And then Galileo says, no, it's not all about heaviness. There's something else happening here. And he was able to demonstrate that all objects fall at the same rate. Let me show you more about his argument why things fall at the same rate. Okay? Or in fact, no, I think actually he didn't really know why that was true. Also, this story about him being at the top of the Tower of Pisa is probably apocryphal. It probably didn't happen because we're going to learn later that heavy things do fall at a different rate than light things due to air resistance. But if he was standing here, you know, if he's dropping things off the first balcony, then definitely they're going to hit the ground at the same time. In the same way that things off the J building would hit off the J building balcony would hit the ground at the same time, just because things are moving slow enough where air resistance is not being really significant yet. But it fell to Isaac Newton to really explain why it is that objects of different masses fall at the same rate. And it came about because Isaac Newton thought of his famous law, F equals ma. He thought of F equals ma, which means acceleration is force over mass. And then you do this incredibly simple thought experiment. You know, let's say I have some mass m. Alrighty. Let's get the acceleration of that mass m. Well, you tell me, at Earth's surface, what is the force acting on that mass m? Yeah, mg, right? Mass times the acceleration of gravity. Alrighty. And, here, let me just do this. Just a second. Acceleration equals force over mass, and the force is mg. And so do you see that this guy's going to accelerate at a rate of g? But consider this mass. Alrighty. Let's do the same thing. Acceleration equals force over mass. Well, the force on this mass is 2mg, right? Mass times gravity, that mass is 2m. This guy's mass is 2m. what do you notice happens to the two m's? Yeah, they cancel, and you get g again. It doesn't matter how big or small the mass is, they end up canceling. So the way that now Isaac Newton can explain this is to say, hey, heavier objects experience more force, but they also have more resistance to changes in their motion. That is, heavier objects feel more force, but they're harder to accelerate. And those two, those two facts cancel each other out, and all things fall at the same rate. And so let me just write that in words, okay? Heavier objects feel more force, but their greater mass makes them harder to accelerate. And that's why it is that Galileo was able to demonstrate that things of differing masses were able to fall at the same rate, because of Newton's F equals ma. But of course, this fact, all objects falling at the same rate, is only true in the absence of air resistance. For example, have you ever seen that famous thing on the moon where the astronaut goes on the surface of the moon and he holds a hammer and a feather and then he drops them both? And the hammer and the feather both hit the moon's surface at the same time? That's because in the absence of air resistance, all things fall at the same rate. But we're now going to be dealing with situations where air resistance is going to be an issue. So let's go to our next thing, which is air resistance. Air resistance. It depends on two things. I have two pieces of paper here. Let me get a quick drink of water. The camera followed me. I have two pieces of paper. Then should I stand over here? I have two pieces of paper. And we're going to have a race to see who hits the ground first. Two identical pieces of paper. You must vote. Do you think this guy's going to hit the ground first? Do you think this guy's going to get the ground first? Or do you think it's going to be a tie? Here we go. Let's have a vote. How many people say this paper will hit the ground first? Okay. Okay, just two of wait, just Gavin. Okay, Gavin and DeAndre. Gavin and DeAndre say this will hit the ground first. Who say this will hit the ground first? Okay, Sahara and Logan and Leilani. Okay, and Mani. Who say it's going to be a tie? Okay, many of you. Okay, here we go. Here comes the race. Are you ready? 1, 2. Looks like Sahara and Logan and Imani and everyone. Whoever voted for that one wins. Good job, Leilani. Good.
It's your dominant hand, so you crumble.
So tell me, why did this guy win the race? Because there was less air resistance. What was it about this guy that made it have less air resistance than this guy? Yes, surface area. So that's the first thing air resistance depends on. It's the surface area. And actually, air resistance is a lot more complicated than that. I'm going to say a few more words, even though that's not even going to tell the whole story. But I'm going to say the surface area profile presented to the air. Surface area profile presented to the air. Because you know it's not just surface area, because I could have something with a large surface area, but if I made it incredibly aerodynamic, you know, this thing has a huge surface area, right? But if it's going that way through the air, it's so aerodynamic that that maybe, you know, there'd be a very minimized air resistance, you know? So it's not just surface area, it's just the profile you present to the air. Air resistance depends on something else. What's the other thing air resistance depends on? And I've actually mentioned it a few times during the course of the semester. Like, under what circumstances do I get to ignore air resistance? Yes?
Is it the height, or like how high you're dropping it from?
Okay, true, that affects it, but tell me more. Because, yeah, when I drop things from high heights, I can't ignore air resistance. When I drop them from low heights, I can. Yes? Yeah, the speed. The faster you go, the more air resistance you feel. How many people have stuck their arm out of the car when the car is going like 75 miles an hour? Yeah, how would you describe the force on your arm? Yeah, high force, right? I've never let my 8-year-old daughter do it, because, you know, you're not supposed to let your little kids put their arms out the windows. But the next time I'm with her, now that I've taught this, I need her to experience that. I need her to know at an early age, when you stick your arm out the window at low speeds, almost no force. Stick your arm out the window at 75 miles an hour, huge force, fun force, a force you want to experience all the time, you know? So I need to do that without her mom in the car. Here we go. So speed. You still have to click that button so that not just that my daughter can't lower the window, that daddy can't lower the window either. Speed. More speed, more air resistance. Great. So air resistance depends on those two things. So now we're going to start investigating air resistance, not numerically so much, but kind of more conceptually. And the first question we're going to ask is, who hits the ground first, the fat parachutist or the skinny parachutist? So here we go. Suppose Mr. Shana and, I don't know, I don't have, and John. Suppose Mr. Shana and John go skydiving, okay? Okay. So here's John. Oops. Here's John. There's no H, right? Yeah. So here's John. Okay. And here's Mr. Shana. So I have significantly more mass than John, okay? And if you were to drop us now, you might think just like those pieces of paper, I've got the bigger surface area than he does, so maybe I would take longer to hit the ground. He would hit the ground first if you dropped us like this. But it turns out we both have identical parachutes, and the surface areas of the parachutes are gigantically huge compared to our individual surface areas. So the fact that I have a little bit more surface area than he is insignificant compared to the fact that our parachutes both have this stupendously large amount of surface area and thus are going to slow us down so we don't hit the ground and die. So here's John's parachute. Okay. Maybe I'll make it like that. So here's John's parachute, and I've got an identical parachute. Okay? So I want to make it clear that this first thing that air resistance depends on is not an issue in this problem. You know, we both have the same surface areas, the same profile presented to the air. The fact that I may have more surface area is insignificant, okay? We're both going to leave the plane at identical times. We're both going to have an initial velocity of 0. Who hits the ground first? You got 3 choices. John, Mr. Shana, or it's a tie. Please think about it, then I'm going to have you vote, and then we're going to talk about it a little bit. Okay, here we go.
Okay, would you like some more?
I'm doing good.
How many people say John hits the ground first? 1, 2, 3, 4. How many people say I hit the ground first? 1, 2, 3, 4, 5, 6, 7, 8. How many people say it's going to be a tie? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. All right. So someone who voted for John. Why John? Why do you think John's going to hit the ground first? Yes, Anais.
Okay, so the way I thought about it, and maybe it doesn't make any sense, but he weighs less. So in a way, it's just, there's not necessarily as much air resistance. While, because, okay, not even thinking, well, yes, thinking about the parachute, that's, they're both the same there. So because he has less weight and mass to him, in a way, it's almost as if it's just the parachute fall, and so it's the same resistance as yours, but in this case, you're also resisting against the air. Yes.
Okay. So you're thinking kind of like I'm resisting the air along with my parachute and he kind of isn't, sort of thing?
Yes.
Okay. Someone who voted for me, Mr. Shana. Why do you think? Yes, Imani.
Because I said, so they're both gonna have air resistance because of the parachute, but because John weighs less, like, there's gonna be more air resistance, but like, Mr. Shana weighs more than John. So like there's more force pulling down, like kind of canceling out with the air resistance. So it'll go faster.
Okay, so Imani's going because Mr. Shana weighs more. She's going, hey, granted, you and John feel air resistance, but because I've got way more gravitational force pulling down on me, that'll have the effect of making me accelerate faster or accelerate more. Okay? Who said a tie? Why does someone say it's a tie? Yes?
I said because like the parachute's so big that it wouldn't even matter like how much mass you guys take out.
Okay. Okay. Great. Hey, before we actually investigate this, let's see if anyone wants to change their vote based on what Anais, Imani, or Jonathan said. How many people now say John is going to hit the ground first? 1, 2, 3, 4. Plus Anais, I assume. I don't know. Do you vote for John still?
I voted for John to begin with.
But do you want to change your vote now?
No, I'm okay.
Oh, that's fine. How many people vote for me? Who say I'm going to hit the ground first? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of you.
Yeah.
Okay. And how many people say it's going to be a tie? 1, 2, 3, 4, 5. Okay, great. Hey, let's go ahead and investigate this. So me and John step out of the hot air balloon, let's say, and initially he's got a weight mg on him, and he has no air resistance on him because he's not moving at all. And same with me. I have no air resistance, but I have this significantly larger weight, okay? So at this point, we're both accelerating down at g, right? Because yeah, he's got a force of mg on him, but his mass is m, and so his acceleration, which is mg over m, the m's cancel, just like I showed you earlier in the period. He's accelerating down at g. Same with me. My weight is a big mg, but my mass is big M, so I do big mg over big M. The big m's cancel, and I'm going down at g. But pretty soon we're falling far enough. We're gaining enough speed. Remember, the more speed, the more air resistance, that pretty soon we're both going to have a significant amount of air resistance. So, like, for example, here's John's weight, but now he's experiencing some air resistance that's opposing his motion. And this air resistance, I hope you don't mind, I'm going to call it R. So he's got a certain amount of air resistance. And let's suppose Mr. Shana has the same amount, same speed. And so since I have an identical parachute, I'll have the same amount of air resistance as John. Okay. But I'm significantly heavier. Oops. You guys okay with that? Well, which direction is he accelerating right now? Say, Logan, tell us.
Down.
Sure, down. Because why? How do I know he's accelerating downward still? Beautiful. The one on the bottom is bigger than the one on the top. He still has more weight than air resistance, so he's going to continue to accelerate downward. He's still going faster and faster downward. Which direction am I accelerating? Yeah, down. I'm accelerating down. But my net force, of course, is significantly bigger than his, but my mass is bigger than his. Until pretty soon, he's going fast enough that his air resistance is exactly equal and opposite to his weight. He's going down so fast that his air resistance equals his weight. Tell me, what is his acceleration now? 0. What's that special name we give to the velocity he has now just achieved? How many people think in terminal velocity? Yeah, that's the velocity you reach such that you don't go any faster. And the reason you don't go any faster is because your air resistance has now equal and opposite to your weight. You no longer have a net force on you. John has reached terminal velocity. Okay. Let's look at Mr. Shana. I'm going the same speed as he is. So I've got the same air resistance on me. But look at my weight. Have I reached terminal velocity?
No.
Heck no. I'm nowhere near terminal velocity. My weight is still significantly bigger than the air resistance on me. Which means, what am I going to do?
Keep accelerating.
I'm going to keep accelerating. I'm going to go faster and faster and faster until when? No, not when I hit the ground. Go ahead. Yeah, till I hit my terminal velocity, right? I got to keep going faster and faster to make that air resistance bigger and bigger until finally I find myself in this situation where here's my weight and I'm going so darn fast that I finally achieve this gigantic air resistance, and now I get to hit terminal velocity. Air resistance equals the big mg. I get to have terminal velocity. But what's going to be true about my terminal velocity versus John's terminal velocity?
Yours is greater.
Do you see that mine's going to be way greater? My terminal velocity is going to be huge. I had to go super fast to achieve a big enough air resistance to balance my gigantically huge weight. You guys okay with that? So let me ask you again, who's going to hit the ground first, me or John? How many people vote John's going to hit the ground first? How many people vote Mr. Shana's going to hit the ground first? Well, good for you guys, all of you. Yeah, absolutely. I'm going to hit the ground first. And I'm going to tell you, I'm going to ask this question on your next test. And I'm hoping someday they'll ask this question on an AP exam, because I think it's an incredibly cool question. So I'm going to present to you one possible answer. But any answer you give is good as long as you include everything, you know? Okay, who hits the ground first? Mr. S. Why? Because he needs more air resistance to balance his greater weight. He needs more air resistance to balance his greater weight. He must go faster to achieve that higher air resistance. Thus, his terminal velocity is bigger than John's terminal velocity. is bigger than John's. So that's the name of that tube. Let me do something else here. Oh, does anyone have any questions or comments about this? Has anyone ever gone to that place? I think it's in the Ontario Mills Mall, where it's like this wind thingy where you go in there and the wind is really high up and you're floating. Has anyone ever done that? Really? How does it feel?
It was weird. I don't know, I felt like I was standing, but then at the same time I didn't. And it was weird.
Okay. So like you're standing, but you're in midair. How did you like it? What did you think of
It
it?
was terrifying. I was like 10 at the time and I started crying. I had 2 turns, but I gave my other turn to like some random kid because I didn't like it.
Yeah. I don't think I'd like it now. Yeah, it's just that what they're doing is they're trying to, what do you call, simulate this situation. Or do you need you need something to focus on?
There we go.
Yeah, exactly. I mean, I don't know if it just doesn't seem that fun to me, but I think there's a lot of kids who just live for that. But I don't know, you know. But anyway, that's what they do. They shoot air at you, and you're held aloft by air resistance. But not because you're falling through the air, but because they're shooting the air up really fast at you. Okay, well, hey, let's look at a couple of graphs. Time, velocity. Okay. So let's say I skydive, or I'm not even skydiving. I've just, you know, here's my hot air balloon. Here's the gondola of the hot air balloon, and I'm just going to step out of that hot air balloon. Okay? So I step out of the hot air balloon and just start falling from rest. Alrighty? What's my velocity versus time graph going to look like? Someone describe it to me. So I'm falling from a really, really high height. What's my velocity versus time graph going to look like? Go ahead.
You're saying the bottom up, go up diagonally to the top right.
Okay, so Brandon's going, I'm going to go up like this, right? Okay, so are you guys agreed that I'm going to start at the origin?
Yeah.
Because my initial velocity is 0? And he's saying I'm just going to go, woo. But tell me, what's going to happen to me eventually?
You start going faster.
Okay, I'm going to go faster and faster. Until when? What's that? I'm going to hit terminal velocity. So what's this curve going to have to do? Yeah, it's going to have to straighten out. It's going to have to plateau, correct? And it's going to plateau at my terminal velocity. Terminal velocity. So if this is my terminal velocity here, my graph is going to have to plateau at the terminal velocity. And let me ask you another question. Is this graph going to look... Is my graph going to look like a straight line, or a happy face, or a sad face?
Happy face.
Sad face. You're increasing and decreasing rate.
Happy face?
Well, let me ask you this. Gavin, why do you say sad face?
Because you're going to end up increasing and decreasing rate.
Say that again?
You're going to go up and then it's going to slowly approach that asymptote.
Okay, well let me ask you this. The slope of my graph, give me a number. What should the slope of this graph be? Remember, slope is rise over run, meters per second per second. What's the slope of my graph going to have to be initially? Why do you say 9.8, Noel?
Because the acceleration is going to equal your force over the mass, and the force is gravity.
Yeah, it's 9.8, baby. When you first step out of that balloon and you have no speed, you're in free fall. Your acceleration's 9.8. So I just want you to know that initially, this slope is going to have to be 9.8 meters per second squared, right? But as you start gaining more speed, right, and as air resistance starts taking the net force, making your net force get smaller and smaller until the net force becomes 0, your acceleration should be lowering as well. So you're going to start off with a slope of 9.8, but you're going to get less and less acceleration as the air resistance force gets bigger and bigger, until pretty soon you get right there, and now you're just moving at terminal velocity. Okay? So I want you to see that's not a straight line. If you drew this as a straight line, you get no credit for that. You got to be aware that you start off with a slope of 9.8, and then your slope gradually decreases as your acceleration is decreasing, until finally you get to here, your acceleration is 0. You see? So hey, let's do another graph. How about acceleration versus time? And let's say this is the time when you hit terminal velocity. Someone describe to me, where should my acceleration versus time graph start? At the origin? Tell me, what should my acceleration start at? Good, Cole, tell me.
9.8.
Thank you very much. It starts at 9.8. My acceleration starts at 9.8. And by the time I hit terminal velocity, where should my acceleration be? 0. And now here's the next question. Should I connect these two dots with a straight line, a happy face, or a sad face? What do you think?
Happy.
Happy face? So Pooja's saying that my acceleration is going to, from the very start, have this precipitous decline, and then go into the time there. Does anyone have an argument for another thing besides happy? What do you think? Is my acceleration going to have a precipitous decline? That is, when I first step out of that balloon and I'm going, 5 meters per second, 10 meters per second, 15 meters per second. Does that mean I'm going to have a precipitous decline in my acceleration? Fatima, you are shaking your head. Why do you shake your head?
Well, because at first your acceleration is going to increase before it starts to decrease.
Well-
Before it hits zero.
Well, let me ask you this. Is my acceleration increasing? What's my acceleration when I first step out of the balloon?
9.8.
Good, and is that going to get bigger? No, it's just going to stay 9.8, right? As long as air resistance can be ignored, I'm just going to maintain an acceleration of 9.8, right? So for the first several seconds, my acceleration is going to be 9.8 because I'm just not going fast enough for air resistance to be an issue, right? So I just want you to see, initially, I'm going 9.8 until I start going faster and faster and faster. Then you're going to see my acceleration precipitously decline, right? As I go faster and faster and faster, air resistance gets bigger and bigger, my acceleration gets smaller and smaller, because the net force on me is getting smaller and smaller until I get to 0. So I think that's a more accurate graph of acceleration versus time. Here, we're at small speeds. So we're at small speeds, so we're maintaining our 9.8 acceleration. Pretty soon we get to high speeds, and we're starting to really lose our net force. Okay, let me ask you this last question. I've got a guy, and he's going to shoot a gun. And the initial velocity of that bullet is 300 meters per second. The bullet goes up, reaches a maximum height, and comes back down. What's the speed of the bullet going to be? By the way, 300 meters per second, that's like 650 miles per hour, or something like that. Okay? If that bullet hits the ground, how fast is that bullet going to be going? How many people say it's going to hit the ground going 300 meters per second? Same as going. Okay, I'm going to tell you no, because of air resistance, it isn't going to be 300. Now tell me, why not? Why isn't it going to hit the ground at 300 meters per second? Because of air resistance. Good, Roger? Oh, I thought you had you. Okay, what's that, Nicole?
It's going quickly.
Okay. Well, it's going quickly that way. It reaches its maximum height where it's momentarily at rest. Now it's falling faster and faster and faster, except what's different about this part of the trip?
It reaches terminal velocity.
Thank you. It reaches terminal velocity. Here, it doesn't reach terminal velocity. It starts at 300 meters per second and loses all of its velocity till it reaches the top of its travel. But once it starts falling, it's not going to obtain 300 meters per second unless you're on the moon, where there's no air resistance. But what's going to happen is at some point, you're going to reach terminal velocity. And terminal velocity for a bullet is, I don't know what it is exactly. I think it's something like 60 meters per second. Terminal velocity for a bullet is 60 meters per second. You see? So do you see that bullet went out of my gun at 300 meters per second? Well, that bullet's going to hit the ground at about 60 meters per second. Has anyone ever seen that Mythbusters episode where they fire a gun in the air? Because there's that myth that if you fire a gun straight up in the air, the bullet will come down and hit a roof and put a hole in the roof, you know, and kill the people inside. But has anyone ever seen that Mythbusters episode? You know what happened? They fire the bullet in the air. When the bullet hits the ground, they had the I don't know, the skin of a pig or the hide of a pig. The bullet did not even penetrate the pig's hide. The bullet wasn't going fast enough. That is, if you fire a gun straight up in the air, the bullet will come down on your farm. If it hits your pig, it won't even hurt your pig. I mean, it'll hurt him. The pig will go, ow, you know. But it's not even going to penetrate his hide, you see. And that's because the bullet reaches terminal velocity. So that's why, what's it called? Oh, okay. But you're just wanting to chew quietly, that's fine. So you guys, okay, if you're going to shoot, let's say you want to celebrate a military victory, or you want to celebrate a holiday, and you want to shoot your gun in the air. How should you shoot your guns? Straight up. And whenever you see shots of like the Arab countries where they celebrate by shooting their gun straight up in the air, they're doing it right. They know their physics, right? Now the problem is Americans don't know their physics. So when they celebrate New Year's Eve, you know what they do? They shoot their guns horizontally. And if you shoot a gun horizontally, what's going to happen? You're going to kill somebody. The bullet's going to go 50 or 100 yards and hit someone and kill them, right? Because you don't give that bullet a chance to lose all of its energy and then reach terminal velocity. You don't give the bullet that chance. You fire horizontally, you kill people. So remember, if you're going to fire a gun, be an Arab, don't be an American. That's why America, we had these public service announcements. Don't fire your guns at New Year's Eve, you know? Yeah. And so, tell me, what takes more time? Is the time up more or the time down more? Which takes more time? Yeah, hope you see that it takes more time. It takes more time to come down and less time to go up. Because coming down, you reach terminal velocity. Going up, you don't. You just start at 300 and lose your velocity till you get to 0. But you spent a lot of this time, going upward at these elevated speeds that you never achieve on the way down. All right. Well, hey, that's it for air resistance. Just remember, fat parachutist hits the ground first. Always think about terminal velocity. And good luck, you guys.